In this video, we will cover an introduction to scientific notation. Let's start with a couple of quantities. First, the diameter of the moon. So if we stood on one point on the moon and drilled right through the moon, right through the center to a point on the other side of the moon, how far would that be in meters? Turns out 3,500,000 meters, approximately. And how about diameter of an electron, one of the tiny particles floating around the nucleus of an atom? Also in meters, diameter of an electron is about this, 5 quadrillionth of a meter, or 5 femtometers you could call it. Now these are quantities that do come up in science quite a bit, so it can be useful to have a way of writing numbers without having to write all these zeros. And if you encounter a question where you're actually working with a few of these large numbers, or a large number and a small number, for example, how many electrons will fit along the moon's diameter, there even turns out to be a way that we can represent these numbers without all those zeros, and the way makes it a little bit easier to accomplish some of these calculations, like the division we would do in this problem. First, let's talk about large numbers. And for our first example, we'll use 1 million. Now, the idea behind scientific notation, it's actually kind of similar to something that we do already, just with words, that we could say this number is 1 million. All those zeros, those 6 zeros we know equals a million, so we've brought that 1 over and just said 1 million. But what I want you to think about when it comes to scientific notation is, how do we get large numbers? Think about starting with 1 and multiplying by 10. Remember what happens when we multiply a number by 10. The result is that we just end up sticking extra zeros onto the end of the number. And then if I multiplied 10 times another 10, it would equal 100, a 1 with 2 zeros. So looking at this number 1 million, I could think about each of these extra zeros as being a result of multiplying by 10. So I could say that 1 million is really 1 times 10 times 10 times 10 times 10 times 10 times 10. But if I wrote out all those tens, I haven't really helped myself in terms of coming up with a quicker way to write these large numbers. So how could we write this repeated multiplication of 10? And you are right if you're thinking about exponents. So 6 of those 10s multiplied together, we could say is 10 to the 6th. So this number 1 million looks like this in scientific notation, 1 times 10 to the 6th. And the idea is we pull out that number part, the digit that's not a zero, and then all those other zeros we think about, well, how many tens did we have to multiply to get all those zeros to show up? Let's do one more quick example, 32 million. And another reason for me showing you this example is to show one detail about scientific notation that we really have to be careful about. So 32 million, you would say, in words I could put the 32 and then the word million. So in scientific notation, you might say, I have my 32, and then my 6 tens that would bring my 32 up to 32 million when I do that multiply. Now the fact is, when you work with a set of several numbers in scientific notation, it's easier to do calculations and to compare those numbers when the number part in scientific notation is kept small enough to be a number that's in between 1 and 10. And in fact, we don't even like to use 10. So some number greater than or equal to 1, but less than 10. So how do we handle this, that we have a 32, definitely a number much larger than 10, too large that we would want to use in scientific notation? So now think about, what if I did this multiplication, 3.2 times 10? Hopefully you're remembering that multiply by 10 doesn't just put a 0 onto the end, but with decimal numbers we think that it moves the decimal point one place to the right. So 3.2 times 10 equals 32. So if I said don't use 32 but use 3.2, how many times 10 do we have if we go from 3.2 up to 32 million? So we'd need 110 to get us up to 32, and then 6 more. So 3.2 times 10 to the 7th equals 32 million. We're going to get to a couple of examples pretty quickly, but what I want you to think about going forward is that we're not going to focus just on all the zeros we see, but we'll focus more on this idea of moving a decimal point. Let's go back to the number 3,500,000, our diameter of the moon in meters, and let's take another large number for an example, 787 billion, which was the number of dollars in the stimulus bill passed by Congress back in February 2009. 787 billion. Many, many zeros, 9 of them there. Now, my approach when it comes to scientific notation is to think about how many times am I moving a decimal point. So first detail that we should cover is, well, where are the decimal points currently in each of these numbers? With these numbers, the decimal points are actually right on the tail end, and we don't usually write those numbers unless we actually have decimal numbers after that point that we want to include. But we should definitely understand that that's where those decimal points currently are. Next, we take just the number part. We can ignore all these zeros for now, but all the other digits that are not zeros, we need to use those as the number part in scientific notation. And remember, we want to keep this a number between 1 and 10, and basically the way to do that is you always put the decimal point right after the first digit. So with 3,500,000, we pull off the 3 and the 5, we're putting the decimal point right behind the 3. Scientific notation will always use times 10 to some power. That's how we're indicating this decimal point moving. So if the point is starting right behind the 3, how many places will it have to move? And remember, each time it moves a place to the right, this is because we're multiplying by 10. So we're moving it 1, 2, 3, 4, 5, 6 places. So in scientific notation, that means we just multiplied by 10 6 times. So 3,500,000 in scientific notation, 3.5 times 10 to the 6th. Our other example, 787 billion, so we're pulling off the non-zero digits. It's going to be the 787, and we know to put the decimal point right behind the first digit to keep it a number between 1 and 10, so we're looking at 7.87. Now, if that decimal point is right behind the 7, how many places does it move? Basically, how many times do we need to multiply by 10? And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 7.87 times 10 to the 11th. Let's do another example, 80,000. So we pull off the non-zero digit, the 8, and where is the decimal point? Remember, it's a good thought to have that we always put that decimal point right behind our first digit. So think about the point being right there, right behind the 8. So if the decimal point is right behind the 8, how many places will we need to move? How many times will we need to multiply by 10? So from right behind the 8, we've got 1, 2, 3, 4 jumps we need to make. So we're doing times 10, 4 times. 8 times 10 to the 4th. So we're looking at 1,328,000. And a quick reminder about those commas that help us read these numbers. We're always starting from the right, and every 3 digits we're putting in a comma. So I'd have one right here between 8 and 0. 1, 2, 3, another one right between the 1 and the 3. So a 1,328,000. But let's put it in scientific notation. We have several digits here that we need to bring over. The 1, the 3, the 2, and the 8. And our decimal point belongs right behind that first digit, 1.328. Now with that point being right behind the 1, how many places will we need to move? Looks like 1, 2, 3, 4, 5, 6 places. And so we indicate that by saying we're doing times 10 6 times. 1.328 times 10 to the 6th. Now let's quickly talk about doing these problems in the opposite order. What if we started with a number in scientific notation? How would we write it in a standard form? Well, of course, we just had this example. We know it's 1,328,000, but let's go through the steps. What we'll do is we'll take those digits, the 1.328, and we're going to bring those down, and we understand that that decimal point is moving for each time we multiply by 10. So if the point begins right here, I need to move it 6 places. After the first 3 places, I've run out of digits to jump. And whenever this happens, we need to just add extra zeros for these extra jumps that we need to make. So I could make 1, 2, 3 jumps over the 3, the 2, the 8. I still need to make 3 more jumps, so that's going to be through 3 extra zeros. And now we can see all of our digits when this number is not in scientific notation. Let's clean it up a little. 1,328,000. Okay, here are 2 quick examples for you to do. So pause the video, work through these 2, and then restart the video, and we'll look through the answers together. The first example, 6.83 times 10 to the 5th. So I'm bringing over the 6, the 8, the 3, and then thinking about moving my decimal point 5 places. The first 2 jumps will take me past the 8 and the 3, and then my 3rd, 4th, 5th jumps are going to be through zeros. So we'll clean this up, and we're looking at 683,000. The next one, 9 times 10 to the 9th, so I'm jotting down the 9. I know that my point currently is right here behind the 9. So my 9 jumps that I have to make are actually going to end up all becoming zeros because I've started right behind the 9, no digits to jump, so each of these becomes a 0, and we'll throw in those commas, and we've got 9 billion.